Today we're going to do the lesson on finding volume where we have a known cross section. So here are the notes. Let's see if this works. My board is not good. Okay, the do now is very important today, because on the do now, we're going to come up with the area formulas for different shapes that you're responsible to know these area formulas. The first one, I don't think you'll have a problem with. It's the area of a square with side S. Okay, so if you had a square, side S, the area of the square would be S squared. The second shape that you need to know is the area of a semicircle, but we want the area of a semicircle in terms of its diameter. Now, if the semicircle is here, the diameter, you would want to take 1/2 pi r squared. And in terms of the diameter, since the radius is equal to the diameter over 2, when you square that, you will have 1/2 pi times d squared over 4. So that gives us the area of a semicircle in terms of its diameter is 1/8 pi, or pi over 8, times the diameter squared. It is 1/2 pi r squared, but we want it in terms of the diameter, which you will see why later. The next one we need is the area of an equilateral triangle with side S. I'm just going to go to a blank page for that. If you have an equilateral triangle, every side is S. When you drop the altitude, that forms two 30-60 right triangles, right? Because in an equilateral triangle, each of the angles would be 60, and the altitude would also bisect the angle up here. Now, you don't really need to know that the area of an equilateral triangle. What you need to know is that you really need to find the height. So what we could use is one of the right triangles. I'll choose the one here on the right. We know that the length of this leg here would be 1/2 S. 1/2 S. So we can solve for h. The height of this triangle, because we need it because the area of the whole equilateral triangle is 1/2 base times height, where the base is the side, but we need to know what the height is. So to solve for the height, let's use Pythagorean theorem. We have leg squared plus leg squared equals hypotenuse squared. And again, we want to solve for h. So maybe we'll square the 1/2 s out first. So that would be 1/4 s squared. We could subtract 1/4 s squared from both sides. So h squared would equal 3/4 of s squared. Taking the positive square root, since the height is a length, the square root of 3/4 s squared would equal rad 3 over 2s. So now to get the area of our equilateral triangle, we said it was 1/2 the base, which was the side, times the height, which is rad 3 over 2 times s. We get the area of an equilateral triangle is equal to rad 3 over 4 times side squared. We're going to put that back. And again, you just have to know these, but it's always nice to know where they come from. Next one we have to know is the area of a right triangle with, it's an isosceles right triangle with hypotenuse S. So area of an isosceles right triangle with the hypotenuse S. Well, again, the area of a triangle is 1/2 base times height. So we'll use one of the legs as the base and the other as the height. We know they're both the same. So let's find out what they are in terms of the hypotenuse S. So if I put here an L for leg, we know from Pythagorean theorem that L squared plus L squared equals S squared. So 2L squared equals S squared. So L squared equals S squared over 2. The length of each leg is going to be the square root of S squared over 2, which is equal to S over rad 2. So now we can fill in the area of our triangle. The area of an isosceles right triangle will be 1/2 the base, which we'll use the one leg for, which is S over rad 2. All right. Times the height, which is the same, isosceles, S over rad 2. So the area of an isosceles right triangle is equal to S squared over 4, where S is the length of the hypotenuse. It's hypotenuse squared over 4. We're also going to need to know what the area of an isosceles right triangle is in terms of its leg, L. Well, that's the easy case. If you have an isosceles right triangle, and we want to know the area in terms of its leg L, again, area of a triangle is 1/2 base times height. So it would just be 1/2. We'd use one leg as the base and the other leg as the height. So we just get L squared over 2. So the area of an isosceles right triangle is also equal to the leg squared over 2. And we need to know both of those. So it's either hypotenuse squared over 4 or leg squared over 2. Okay, those are the area formulas you need to know to attack the kind of problems we're going to look at today. Today, we're going to look at volumes of solids not that are created by revolving a region about some axis, but a solid where every slice has the same shape, kind of like a weird loaf of bread. And the way we're going to do this, just like we've done all with area, we added up an infinite number of the areas of an infinite number of rectangles. Volumes of solids of revolution, we added up an infinite number of the volumes of an infinite number of discs or washers. With these, we get the volume of a single slice, which is its area times its thickness, which will be dx or dy, and we integrate that. So that's why you have to know these area formulas. Okay, let's go ahead to our first example. Okay, so these are the formulas you need to know. Okay. Our first example, find the volume of a solid whose base is the circle x squared plus y squared equals 4. Hopefully you recognize that graph would be a circle. The center is the origin, and whose radius is 2. This is the graph. Y, well, it's not solved for y. It's x squared plus y squared equals 4. If you didn't know that, to put into your calculator, you would have to solve for y. You'd have to break it up, right? That's not a function. Y squared equals 4 minus x squared. And you'd have to graph both y equals the positive and the negative square root of 4 minus x squared. Okay, but we have this solid. Now this is the base. The area in the circle is the base. And growing out of this base, we have slices. These slices are perpendicular to the x-axis, and every slice is a square. When they give you a problem like this, they have to tell you what the shape is, okay, and they have to tell you which way the slices are going. Our slices are going perpendicular to the x-axis. Now I'm just drawing the base of it, but the actual square is sticking out of the paper into the air. Let's pause this for 1 second. To help you visualize this, okay, we have the circle x squared plus y squared equals 2. And growing out of it, we have these squares. And you can see, I put my sample over there, but we'll have little ones and big ones, and if you get over here, we'll have smaller ones. You're trying to find the volume of the solid generated. So we're trying to find the volume of a solid that looks like this. You could add them all up. All right, so we know what the basic cross-section looks like, and now we're going to add them up by integrating. Okay, let's go back. Oops. Okay, so you know that all the slices coming out of the blackboard or the smartboard are perpendicular to the x-axis. So if the slices are perpendicular to the x-axis, when we go to find the volume, we're going to integrate area times thickness. The thickness of each slice is going to be a small change in x. It's going to be dx. Now, we have to know the area for the shape they're talking about. In this case, every slice is a square. So we know that the area for a square is the length of the side squared. Now we have to fill in what that length would be. Well, if you look at the sample strip I drew, it's vertical. So you know that we need to take y top minus y bottom. We want that's the length of the side of the square. So y top is y on the top half of the circle. Y on the top half of the circle is equal to the positive square root of 4 minus x squared. Whereas y bottom is y on the lower half, which is equal to the negative square root of 4 minus x squared. So we're going to get the volume by squaring the length of the side. The length of the side is equal to the square root of 4 minus x squared minus the negative square root of 4 minus x squared, which is simply going to be 2 square roots of 4 minus x squared. Now we still have to square that, and we still have to get our limits of integration. So in this problem, we're going to add up all these slices. Think of it as a strange loaf of bread, starting at the smallest x, which would be negative 2, and going over to the greatest x, which would be 2. And we have to square the length of the side. So if we square the 2 radical 4 minus x squared, you square each factor, so you have 4 times 4 minus x squared. You can pull the 4 out. And now all we have to do is find the antiderivative. The antiderivative of 4 minus x squared would be 4x minus 1/3 x cubed. We have to integrate this from negative 2 to 2. So it would give us 4 times, we'll plug in the upper, lower, and subtract. We plug in the 2. 4 times 2 is 8, minus 1/3 cubed is 8/3. We plug in the negative 2, we get negative 8. And we're going to have negative 1/3 times negative 8 would be plus 8/3. So let's combine like terms. 8 minus negative 8 would be 16. Negative 8/3 minus 8/3 would be minus 16/3. So we have 4 times 16 is the same thing as 48/3 minus 16/3. We 4 times 32 thirds, which is equal to 128 thirds. That would be the volume of this solid where every slice perpendicular to the x-axis is a square. A lot of details here, but if you look back at the original, all we're doing when you're trying to find a volume of a solid where every slice is a particular shape, you represent the volume of a single slice, which is its area times thickness. You fill in the area formula for that particular shape, and if it's dx, you're going to be using y top minus y bottom to get the length involved. In this case, it was the length of the side of the square. And if it was dy, we'd be using x right minus x left to find the length involved. Let's try another one. Example 2. This time we want to find the volume of the solid whose base is the region enclosed by y equals x squared. Parabola. Y equals 4. So we see the region enclosed. And the cross sections perpendicular to the y-axis are isosceles right triangles with the hypotenuse in the xy plane. So when you see the slices or cross sections are perpendicular to the y-axis, you just want to give yourself draw a little horizontal line there, because the important thing about that is you know the thickness, because the volume is equal to the sum of the area times the thickness, which when it's horizontal, that thickness will be a small change in y. Now, every slice is an isosceles right triangle, but because the length that we have to use, the length of the segment in the base, is actually the hypotenuse, we need to know the formula for the area of an isosceles right triangle in terms of its hypotenuse. Right, that's how we know which one to use, because there are two for that shape. Hypotenuse. So if you recall, the area of an isosceles right triangle is the hypotenuse squared over 4. Okay. Oh no, it was over 2. Oops, 6. Sorry about that. Okay, pause. Okay. In terms of the hypotenuse, it's that squared over 4. That's right, because it goes in terms of leg, it'd be half leg over 2. Be half leg times leg, it would just be a half L squared. Okay, so it's hypotenuse squared over 4. So we fill in the right area formula. Now we have to represent the length of that hypotenuse. It's horizontal. We're going to do x right minus x left. Well, you're going to have to break this parabola up. If you're on the graph y equals x squared, that means that if y equals x squared, x is going to equal plus or minus the square root of y. If you're over here on the right, where the x's are positive, x equals a positive square root of y. Over here, where the x's are negative, x equals the negative square root of y. When you want to find the length of s, we're going to use x right minus x left. You're going to pull the 1/4 out. So we'll have positive rad y minus negative rad y. It's kind of familiar. So the hypotenuse will equal 2 rad y. So the length of our hypotenuse is 2 rad y. Don't forget we got to square it. When we square that, we get 4y. The 4 I can pull out front, which is going to cancel out that 1/4 that was out there. The only thing we need now are limits of integration. Since this isn't a dy problem, we're adding up all these slices from the smallest y to greatest y. So the y values start here at 0, and they go all the way up here to where y is 4. So this this one is easy enough. We take the antiderivative of y, we get 1/2 y squared. We have to integrate from 0 to 4. So we get 1/2 of 16 is 8, minus 1/2 of 0, which is 0. And we get the volume of this solid would be 8. Hope you'll like this. Okay, let's try another one. This is a nicer. All right. Okay, the next one. We want the volume of a solid whose base is bounded by the lines f of x equals 1 minus x. So that's a line. Y equals 1 minus x would be a line with a y-intercept of 1 and a slope of -1. And the other one is another line. G of x is y equals x minus 1. So this one has just a slope of +1 and a y-intercept of -1. So this is 1. This is -1. So this is g of x equals x minus 1. And then also x equals 0, which is just the y-axis. So we're talking about this region here. And so that's the base. That's the base of our solid. Every slice, we got to see which way it goes, perpendicular to the x-axis is a semicircle. So volume, you're adding up area times thickness. Because the slices are perpendicular to the x-axis, the thickness of each slice is a small change in x. So this problem, all about the x's. The area of a semicircle is equal to pi over 8 times the diameter squared. You see why we wanted the area in terms of the diameter? Because this, what we see here, the length of this strip that I drew here, that's the diameter of the semicircle. The rest of the semicircle is coming out of the board. Let's see if I can get in a little illustration of that, just so you can kind of see what it would look like. I don't know that I can. I'm going to try. Okay, let's just change. Oh, I lost something. Run it. Okay, cool. I just want every shape to be a semicircle. Now the base is the wrong shape. I don't know if I can mess with that here. X values. Yeah, my base is off, but still the whole idea that you can add these up to generate a solid. I don't have this one set up, but that's kind of neat. So back to our problem. So we would have big semicircles over here on the left and working with smaller semicircles there on the right. Now, as far as the pi over 8, we can pull that out front. We just got to figure out what that diameter is. You always have a length in all your area formulas. You have to have 2 dimensions, right? So it'll always be like a length squared or 2 dimensions of a product of 2 different lengths for a rectangle. The diameter is the length of this segment that I drew. So we're going to use y top minus y bottom. Y top equals 1 minus x. Y bottom is equal to x minus 1. And so if we just clean that up in there before we square it, we have 1 minus -1, so that's 2. And we have a negative x minus 2x. So our integrand is going to be the square of 2 minus 2x. Now we want to integrate this from left to right, from smallest x to greatest x. If you didn't see where the x value, where they intersect, you would have to actually set x minus 1 equal to 1 minus x and solve for x. We have 2x equals 2, so x equals 1. So our limits of integration, we'd add up these slices, starting at 0, going up to x equals 1, from x equals 0 to 1. Okay, now we got the setup, we just got to square this out. 8x plus 4x squared. If we square that out, take the antiderivative. So the antiderivative would be 4x minus 4x squared plus 4/3 x cubed. We have to evaluate that from 0 to 1. So we got pi over 8. We plug in the 1. There. We'd have 4 minus 4 plus 4/3. When you plug in the 0, actually all the terms are 0, so we don't have to worry about that. So we have the pi over 8 out here. 4 minus 4 plus 1/3 is just 4/3. So when we multiply, we can simplify this a little. 1, 2. We get the volume is equal to pi over 6. And you're taking advantage of your pause button if I go too fast. All right. I think I have it nicer here. Okay, but that's the idea. When every slice has a particular shape, the volume of a single shape, one slice, would just be the area times thickness. So that's what you're integrating, area times either dx or dy. Okay. One more. I think there's one more. Okay, so now we want to find, the volume of a solid whose base is the area enclosed by the graph y equals ln of x squared plus 1, y equals cosine x, and whose cross-sections are perpendicular to the x-axis, and those cross-sections are in the shape of equilateral triangle. Well, you know we're going to need to use our calculator on this one, because those points of intersection won't be pretty. So we just take out our calculators. And let's take a look at this region. So go ahead and enter those. Okay. So in y1, we're going to put in the ln of x squared plus 1. And in y2, make sure you're in radian mode. Quick little check, yep. y2, we have the cosine of x. And we're looking to see, so hopefully that encloses region. Let's just take a look. Let me try a zoom 6 on that. Okay, there's the ln of x squared plus 1. Wow. Okay, well this is not a good window. Let's zoom in around the origin. So I'm going to press zoom 2, enter. Okay, so now we can see a little better what that region is. So that's the base of our region. Let me just take a little picture of that and bring it over. So let's see, tools. Copy that. And paste. Okay. So this is the base of our region. Make that a little bigger. And now if you take slices perpendicular to the x-axis, so going this way, these slices are all equilateral triangles. So the rest of the equilateral triangle is coming out of the board. Right? You're only seeing the base, which we call x. So the volume of this solid would be the sum of area times thickness. Because the slices are perpendicular to the x-axis, the thickness is a small change in x, so it's the x. Now the area of an equilateral triangle is rad 3 over 4 times the length of the side squared. We'll pull out the rad 3 over 4. And now we got to figure out how we can represent the length of the side of our equilateral triangle, which is going to be the length of the strip we drew. It's vertical, so we're using y top minus y bottom. Y top, this is the cosine curve. Y bottom That's the ln of x squared plus 1. So our integrand is the square of cos x minus ln of x squared plus 1. Now, for our limits of integration, we have to go back to the calculator because we want to go from smallest x, which is whatever that is, I'm going to write down a here, to greatest x, which is the x-coordinate of that point of intersection, which I'm going to call b. That looks like an even function, so I'm sure they're opposites. Let's go back to the calculator and get those. Go to the calculator. We're going to use the intersect feature. Second trace, that's your calc menu. Option 5. First curve, it's telling you it's on ln of x squared plus 1 if you look in the upper left-hand corner. You just hit enter. Second curve, yes, the second curve is the cosine of x. Enter. Now, when it says guess, say I want this one over here. I'm going to get this one first. You move over there with the arrow keys. Yes, now I'll hit enter. And it's giving me that x-coordinate is negative 0.9158577. When you get a value on the calculator, jot it down, but you want to store those values. So what you do to store that x value is you hit second mode and hit store alpha a, enter. Now whenever you want to use that number, we're just going to have to use a. And let's go get the other one, even though we know what it's going to be. We go back to our graph. We find the other point of intersection, so second trace, option 5, first curve, enter, second curve, enter, guess. Let's go over to where it looks like it's close to the second point of intersection over here, and hit enter. And yeah, it's positive 0.915857766. I want to store that in alpha b. So I leave this screen, second mode, and just hit store right above the on button, alpha b, enter. It's important when you store things, hit enter. And then I would jot down on my paper, in fact, let me just go ahead and copy this little screen, tools, screenshot, and then copy, back to our work. Edit. Okay. So you would want to write down, if you're just going to write an A and a B here, you want to have on your paper that A is equal to negative 0.91585766591, and B, now we're going crazy with all the digits, but it's kind of nice to be as accurate as possible. 0.91585766591. Now this is the beautiful part of problems like this. To get our answer, we're not actually going to take the antiderivative. You wouldn't even be able to take the antiderivative of this one after you've squared it out. You don't know how to integrate ln. And so what you're going to do is you're going to enter it into the calculator. But watch how nice this works out. We go to our calculators. Now remember what was outside. We had the rad 3 over 4. So I'm going to type that first. Square root of 3 goes to square root over 4 times the integral of, so math 9. Now remember what we were integrating? Cosine x minus the ln of x all squared. So I had my cosine x in y2. So y2, ours, one of ours, function y2 minus the ln of x squared plus 1, which I had stored in my y1. Stayed up there. So I'm just going to type in bars. You can actually write it out again if you want to, instead of doing the y1, doing the y1. The big thing is don't forget you want to square this. So square, that's what you're integrating. And then you have comma x, comma lower, which we stored in a, so alpha a, comma upper, which we've already stored in the calculator, alpha b. Alpha b. So this will give us the volume of our solid. And we want to be accurate to at least 3 places after the decimal. So for our final answer, we will write 0.397. Hope you like this. Bye. Where is my